The full time-dependent Schrodinger equation for a single particle in one dimension is I(h bar partial derivative of psi of xt with respect to t equals negative h bar squared over 2m times second partial derivative of psi of xt with respect to x squared plus v of x psi of xt. It looks a lot like a wave equation but with a complex amplitude. To find states that have a single fixed energy called stationary states, we try to separate the space and time parts. Assume psi of xt equals psi of x times t of t. Substituting this product into the full equation and dividing both sides by psi times t gives I(h bar 1 over t derivative of t with respect to t equals negative h bar squared over 2m1 over psi second derivative of psi with respect to x squared plus v of x. The left side depends only on time, the right side only on space, so each side must equal the same constant, which we call the energy E. I(h bar derivative of t with respect to t equals e times t leads to t of t equals e to the negative I e t over h bar. Negative h bar squared over 2m second derivative of psi with respect to x squared plus v of x psi equals e psi. The second equation is the time-independent Schrodinger equation, abbreviated TISE. It is the quantum analog of a classic vibrating string equation. The shape psi of x of the standing wave is set by the potential v of x and the allowed energy E. A helpful analogy is a guitar string fixed at both ends. The string can only vibrate at certain frequencies called harmonics because the ends force the displacement to zero. In quantum mechanics, the potential walls do the same. They enforce conditions on psi of x that allow only discrete energy values. The TISE is the starting point for almost every textbook problem in engineering physics because it lets us treat the particle's spatial behavior without worrying about its time evolution. Time merely adds a phase factor, e to the negative IET over h bar. Boundary conditions are the rules that tell us which psi of x are physically acceptable. The key ideas are: infinite wall, hard wall. If v of x approaches infinity at some position, the particle cannot exist there, so the probability density must be zero. Mathematically, psi of x equals 0 at that point. This is the same as a guitar string that cannot move at a clamped endpoint. Finite step or barrier. If v of x is finite but changes suddenly, the wave function itself must stay continuous, no jumps, because otherwise the probability would be infinite in an infinitesimally small region. The first derivative d psi by dx must also be continuous unless the potential contains a delta function. This follows from integrating the time-independent Schrodinger equation across an infinitesimally thin region and noting that the second derivative cannot contain a delta unless v does. These conditions turn the differential equation into a quantization rule. Only certain values of the energy E make it possible to match psi and d psi by dx on both sides of the boundary. For example, in an infinite square well, the condition psi equals 0 at x equals 0, and x equals L forces the sine function to have nodes at the walls, which only happens when the wavelength fits an integer number of half waves inside the well, yielding discrete energies. The one-dimensional infinite square well, also called a particle in a box, is the simplest textbook example. V of x equals 0 for 0 less than x less than L. V of x equals infinity otherwise. Because v is infinite at the walls, psi of 0 equals psi of L equals 0. Inside the well, the time-independent Schrodinger equation reduces to minus h bar squared over 2m times the second derivative of psi with respect to x equals e psi, or the second derivative of psi with respect to x plus k squared psi equals 0 with k equal to the square root of 2me divided by h bar. The general solution is psi of x equals a sin of kx plus b cos of kx. The wall at x equals 0 forces b equals 0, and the wall at x equals L forces sin of kl equals 0, which implies kl equals n pi with n equals 1, 2, 3, and so on. Thus the allowed wave functions are psi sub n of x equals square root of 2 over L times sin of n pi x over L, where the prefactor square root of 2 over L makes the function normalized. Integral from 0 to L of absolute value of psi sub n squared dx equals 1. The corresponding energies are obtained from k. E sub n equals h bar squared k squared over 2m which equals h bar squared pi squared n squared over 2ml squared. Example problem. A particle of mass 9.11 times 10 to the minus 31 kilograms, an electron, is confined in a box of width L equals 1 nanometer. Find the ground state energy. Plug in E sub 1 equals h bar squared pi squared divided by 2ml squared, which is approximately 1.055 times 10 to the minus 34, squared times pi squared divided by 2 times 9.11 times 10 to the minus 31 times 1 times 10 to the minus 9 squared, which is approximately 6.02 times 10 to the minus 20 joules, or 0.376 electron volts. The result shows that even a tiny box forces the electron to possess a non-zero kinetic energy, an illustration of the zero-point energy. Explanation: when the walls are not infinitely high, the particle can leak a little into the surrounding region, producing bound states with energies below the top of the well. Consider a symmetric finite well of depth V0 greater than 0.5 width A. V of x equals negative V0 for absolute x less than A. V of x equals 0 for absolute x greater than or equal to A. Inside the well region 1, the time-independent Schrodinger equation gives d squared psi by dx squared plus k squared psi equals 0, with k equals the square root of 2m times open bracket e plus v0 close bracket divided by h bar. Outside the well region 2, the energy E is negative relative to the outside, so d squared psi by dx squared minus kappa squared psi equals 0, with kappa equals the square root of 2m times absolute E divided by h bar, leading to exponentially decaying solutions. Applying continuity of psi and d psi by dx at x equals yields two transcendental equations, one for even states, one for odd states. Even k times tangent of Ka equals kappa, odd negative k times cotangent of Ka equals kappa. These cannot be solved algebraically. Instead, we plot the left-hand side and right-hand side as functions of k or E and look for intersections. Each intersection gives a permissible energy. Example, let m be the electron mass, A equals 0.5 nanometers, and V0 equals 10 electron volts. Plotting the even equation shows two intersections meaning two bound even states, and the odd equation gives one intersection giving a total of 3 bound states. The energies are typically found numerically, for example using a spreadsheet or a root-finding routine. The quantum harmonic oscillator models a particle attached to a spring, the same way a mass on a spring oscillates in classical mechanics. The potential is V of x equals half m omega squared x squared, a parabola that grows without bound. Plugging this V of x into the TISC leads to the differential equation minus h bar squared over 2m times d squared psi over dx squared plus half m omega squared x squared psi equals E psi. The clever step is to introduce a dimensionless variable xi equals alpha x, where alpha equals square root of m omega over h bar. After some algebra, the equation becomes the Hermite differential equation, whose solutions are the Hermite polynomials h sub n of xi. The normalizable wave functions are psi sub n of x equals n sub n times h sub n of alpha x times e to the minus alpha squared x squared over 2, with n sub n equals alpha over pi to the 1/4 power times 1 over square root of 2 to the n times n factorial. The corresponding energy levels are E sub n equals h bar omega times open bracket n plus half close bracket, n equals 0, 1, 2, and so on. Note that even the lowest state n equals 0 has energy h bar omega over 2, the famous zero-point energy, reflecting that the particle can never be completely at rest because of the Heisenberg uncertainty principle. For a molecular vibration with omega equals 2 pi times 10 to the 13 radians per second, the spacing between adjacent levels is h bar omega, approximately 6.6 times 10 to the minus 21 joules, approximately 0.041 electron volts, which is observable in infrared spectroscopy. Tunneling describes a quantum particle crossing a region where its classical kinetic energy would be negative. Consider a rectangular barrier of height V0 and width, with a particle of energy E less than V0 approaching from the left. Inside the barrier, the TISC gives a decaying solution psi of x proportional to e to the minus kappa x, where kappa equals square root of open bracket 2m times open bracket V0 minus e close bracket over h bar. Matching psi and its derivative at the two edges, leads to a transmission coefficient probability of crossing that for a thick barrier kappa, a much greater than 1 simplifies to T approximately e to the minus 2 kappa A. Example: an electron mass 9.11 times 10 to the minus 31 kilograms with energy 1 electron volt encounters a 5 electron volt barrier that is 0.2 nanometer wide. Kappa equals square root of open bracket 2m times open bracket v naught minus e close bracket over h bar equals square root of open bracket 2 times 9.11 times 10 to the minus 31 times open bracket 4 times 1.6 times 10 to the minus 19 close bracket divided by 1.055 times 10 to the minus 34 approximately equals 1.0 times 10 to the 10 per meter. 2 kappa equals 2 times 1.0 times 10 to the 10 times 2 times 10 to the minus 10 equals 4. Therefore, T approximately e to the minus 4 approximately 0.018, that is about 2% chance of passing through. This tiny but non-zero probability explains how modern devices like tunnel diodes and scanning tunneling microscopes work. A stationary state psi sub n of x is called normalized when its total probability is 1. Integral from minus infinity to infinity of absolute value of psi sub n of x squared dx equals 1. Normalization fixes the overall constant in the wave function, for example the square root of 2 over L factor in the infinite well. Two different eigenfunctions with different quantum numbers are orthogonal. Integral from minus infinity to infinity of psi sub n star of x times psi sub m of x dx equals 0. For n not equal to m, this follows from the Hermitian nature of the Hamiltonian operator, and is similar to how sine and cosine functions are orthogonal in Fourier analysis. The set of all normalized eigenfunctions is complete, meaning any reasonable wave function psi of x can be expanded as a sum or integral of them. Psi of x equals sigma sub n of c sub n times psi sub n of x, with c sub n equals integral of psi sub n star of x times psi of x dx. In engineering terms, the eigenfunctions act like a basis set for the space of possible quantum states, just as sine and cosine form a basis for signals in signal processing. Exam questions on the Schrodinger equation often test the ability to 1. Identify the appropriate potential and write down the TISE. 2. Apply boundary conditions quickly. Set psi equals 0 at infinite walls, match psi and d psi by dx at step potentials. 3. Derive the quantization condition, for example KL equals n pi for an infinite well or tan over k relations for a finite well, and solve for E, often by inspection or using a graph. 4. Use probability current J equals open parenthesis h bar over m close parenthesis times the imaginary part of open parenthesis psi star d psi by dx close parenthesis to check whether the solution describes a bound state, J equals 0, or a scattering state, non-zero J. Quick solve tricks. Memorize the standard results for the infinite well and harmonic oscillator. They save time. For a finite well, rewrite the transcendental equations as f of k equals g of k and sketch both sides. The number of intersections tells you the number of bound states. When faced with a tunneling problem, estimate t with the exponential formula e to the minus 2 kappa rather than solving the full matching algebra. Always verify normalization after you obtain psi. A missing factor will lead to wrong probabilities. These strategies let you move from the abstract differential equation to a concrete answer within the limited time of an exam.